So I have been working on the thesis all along, but I haven't posted any progress video so far. Here it is. Um, I have been working on the thesis as in I was doing the experiments and thinking about why I got the results, uh, such results, and I was more like analyzing the results, and I have a little bit better understanding that I had before. In terms of progress, I was able to emulate the waterborne phantom experiment done by the Jefferson paper, which I discussed previously, I guess. If not, I will discuss in this video. Um, and then there is the beam model behavior, which is kind of tricky to make both beam parameters same in FRED and MC square, but I have made some progress. The idea was to know which dose engine gives greater multiple Coulomb scattering, has shows the behavior of larger multiple Coulomb scattering. Anyway, let's start. This is the lateral profile in water for 150 MeV, and here we can say that okay, both MC square and FRED shows the same multiple Coulomb scattering. This was the behavior that I saw first, and I was convinced that there was no difference in multiple Coulomb scattering. Uh, but I normalized them. Even after normalizing, you would say there is not much of a difference in multiple Coulomb scattering. But please keep in mind that I have made the emittance equal to 0 so that the beam spot is equal to 0. That is, my beam spot is point spot. For MC square, I cannot put the value of sigma x, which is spot width, and sigma x dash, which is angular divergence. Equal to 0 is not possible because of at some point, I guess, it becomes 1 by 0, and which is not allowed by the code. So I have put a small value around 10 to the power minus. The idea is to make it near 0 and make it a point spot. So far so good. Then once you zoom in, you realize FRED has broader multiple Coulomb scattering than MC square. This is quite evident at the entrance. This is just 10 millimeter inside the phantom in the direction through which the proton beam is coming. You can clearly see that FRED has wider lateral profile or lateral peak. Also, you can say why this is not at the center. I was trying to code it to be at center, but because of the normalization, it either comes this way or this way. But anyway, I'll work on the code. But the idea is the multiple Coulomb scattering for FRED is broader than MC square. Then I plotted it at the center of the entrance of the phantom and the bragg peak. So this profile at 80 millimeters inside the phantom is between the bragg peak and the entrance of the water phantom. Here also we can see that the lateral peak is broader than MC square, and at the bragg peak too the profile is broader, but in water it's almost the same, you can say, but we will check that in air as well. And of course this is for as I said, emittance and sigma almost equal to 0. Then I check the lateral profile at in air. again putting emittance and sigma almost equal to 0. Here at the entrance, as we saw in the water, the FRED gives broader multiple Coulomb scattering, while FRED MC square gives narrower scattering. And at the Bragg peak, that was not quite evident in water, but it's quite evident in air that FRED spreads more than, I mean, protons in FRED spreads more than MC square. Now we take one central voxel and shoot a proton, not one proton, like 1 million protons, through it to understand the behavior of how the energy is getting deposited. Again, this is not integrated depth dose, it is just depth dose along that voxel, along the central line. You can clearly see the trend that, of course, at the surface, the dose will be high for a single voxel. At the surface, for a single voxel, the dose will be high because millions of protons are coming, and as they enter the phantom, those energy gets scattered because of multiple Coulomb scattering. So the dose goes down here and here as well. And at the Bragg peak, around 150 millimeter, you get the Bragg peak, which is um, evident, which is what we should expect. And as the voxel size increases, this almost behaves like a big cube. So you see the profile like a integrated depth dose. Also, you might notice that with increasing voxel size, the the size of the cube decreases, because now one voxel is of 2 millimeters, and this here is the numpy indices. So you divide 300 by 2, you get around 150. You divide 300 by 4, you get around 75, so and so. So the depth decreases. That doesn't mean that the peak is at 25 um, millimeter, but rather around 25th, in the 25th voxel inside the cube. I hope I'm making sense. One thing to notice, which is quite not expected, is that in MC square the dose starts at 0, which should not be the case. And I thought it about a lot, and after multiple hit and trial and try to understand why it's happening. Is it because of dose to water, dose to medium? And what I've realized, that both of the dose engines, they calculate dose to medium. um, so what was the cause? And I just recently realized, yeah, that's wrong. MC square so smoother entrance, that is not expected. Fred is okay. I'll tell you the reason. So this is the expected characteristic or feature of the dose that should be deposited in a single voxel, which was evident in FRED but not in MC square. And after, yeah, it took me some time, I realized that FRED's and MC square's coordinate system are not the same. That was one big assumption. So it was post processing problem from my side, and my assumption that the coordinate axis or the geometry will be the same. It's not. what is happening is the center of MC square cube, the cube is 1 millimeter ahead of Fred's. So for Fred, the center is at 150, comma 150, comma 150. Um, for the case of for the case of a cube whose total size is 300 millimeter cube, but for MC square it's 149 in the z direction, rest is 150, 150. And the moment I put that, I got this profile, which was, yeah, that was some progress I made. Anyway, let's move forward. I will also have to study how this profile changes with increasing the voxel size, and I'll find out. So anyway, this was a big progress, and this is expected behavior as this one. Now, the next experiment was to see how protons behave in a heterogeneous medium. You notice that first the bragg peak appeared in the bone, which bone is here, and water is on this side, same case here. So at first you will see, in here you see, first you get the bragg peak in the bone here as well, and then in the water, and then in the water. So you get two bragg peaks, which was quite interesting observation, and I was really happy that I was able to reproduce this. Um, so let's study the characteristics. Here is my the water and bone, and there are my proton beams coming, which was in 40 by 40 grid size, that is 1600 proton beamlets. And yeah, the phantom size is 100 centimeter cube, just to be convenient. Otherwise, if I take 300 millimeter cube of water and bone, plus I have to simulate 1600 beamlets, it takes a huge number of time. As a result, I chose this, and I also reduced the energy to 100 MeV. There you go, 100 MeV bone water phantom normalized, and you see the profile, the two bragg peak. The first bragg peak, this one is in bone and this one is in water. One thing to notice is the bone bragg peak is greater than the water bragg peaks in terms of say magnitude. But this is because the stopping power is larger, and also if you increase the volume of water here, the peak will increase as well. I noticed this while doing the experiment, because more number of photons will deposit energy in the water. As a result, this peak will rise. And although here it seems like bone takes a lot less space, but in the simulation the bone took around 40 millimeter of space in 100 millimeter cube of water, or 40 millimeter cube of bone and 60 millimeter cube. It's not adding up, but in terms of here, so this is 40 millimeter of bone and this is 30 and 30 millimeter of water, or maybe less. I am not sure, but maybe plus minus 5 millimeters of difference there could be. Also, the stopping power of bone is larger than water. You see higher bragg peak, but if you increase the volume of water, this peak rises too. Another thing that is quite noticeable is the bragg peak in bone do not agree in both those engines. they differ by at least 5 millimeters, while in water they may be differing by maybe 2 or 3 millimeters. But I can fix this difference because I just realized, not just like today when I was able to solve the problem of single voxel, that the center in MC square is not as same as FRED, so that can be fixed. So the difference will be, this will be fixed, like this will, they will completely agree, and this difference may decrease to maybe 4 millimeters or 3 millimeters. But that is one area I have to analyze why the difference I'm having this difference in these two dose engines. Next, I have the lateral profile at the entrance in the bone water phantom. So my protons are just entering at the entrance at the depth. So as I showed you before, this is how. So here my protons are entering, and this is the depth, and this is in the bone is also in the in this entire thing is in 3D, of course. Why am I repeating that? um, at the entrance, when I plotted the lateral profile, I see in bone Fred says the dose goes down, and in MC square it says the dose goes up, which is quite confusing. Why? mm, because the stopping power of bone is larger than the stopping power of water. As a result, the dose should be greater in the bone, but Fred is saying otherwise, which is not quite convincing. Yeah, again, I have to analyze that part as well. And then just after the Bragg peaks, that is almost R80 values of of um of those dose in Fred and MC square, I get this profile which agrees almost completely except for this part, again, which I have to analyze this part. But I was able to reproduce the Jefferson papers study, showing this to hump in my study, which was quite a breakthrough for my thesis. Yeah, that was all.